Latitude Media, covering the new frontiers of the energy transition.
In 2025, Georgia Power finished construction on Vogtle Units 3 and 4. These were the country's first new nuclear reactors in 30 years. And to put it mildly, they came in way over budget.
2 new nuclear reactors under construction in Georgia will cost far more than expected. The new reactors will now share a price tag of $28.5 billion, almost double their original cost. The higher costs coming from more construction delays.
The main challenge with new nuclear is really the cost. It's a twofold problem. It's not just high cost, it's high cost uncertainty. And we're in a particularly kind of perilous moment where people are recognizing the value of the fixed, reliable, baseload power that nuclear can provide without the carbon emissions. But if it can't provide it at the cost that people need it to be delivered, it's just not going to be there as a solution.
That's Mike Laufer, the co-founder and CEO of nuclear developer Kairos Power, one of the new guard companies trying to address the problems of industry's old guard. Vogtle illustrates the twin challenges facing nuclear in the U.S. It's not just the staggering price tag, it's the unpredictability of that price tag. That volatility makes sense in an industry that only builds a handful of reactors every few decades. It just doesn't have the track record of repetition to get to cost consistency. But Kairos wants to change that.
So Kairos was really founded on the premise that there has to be a different way to accelerate and drive down the costs through every phase of the process.
The company's approach was a counterintuitive one. First, perfect the non-nuclear parts of the plant, the foundations, the power systems, and the controls. These are the components that tend to drive up costs in a finished reactor.
When Kairos was founded 8.5 years ago, this was an unusual idea. People are like, why would you put all these investments in these big non-nuclear demonstrations? Like, it's extra work in the process.
Second, focus on rapid iteration. This means testing things in months and years, not decades. With a new iterative development approach and a new technology, Kairos set out to change how nuclear is developed in the U.S. But they immediately ran into challenges. For one, the industry's entrenched culture.
If you buy into the iterative process, you don't know what you're going to learn. And so you have to be able to take that information, which sounds simple, but engineers and people, nuclear engineers in particular, like to have everything mapped out, in a very linear process as they go through it. It's very hard to train people to do that.
On top of implementing a new approach to innovation and iteration, they were trying a whole new reactor design, and that came with some serious challenges, the kinds that could derail a project. For example, in 2022, Kairos ordered a reactor vessel for an engineering test unit as a sort of training run of its design, and it didn't work. It wound up testing out of tolerance. In other words, it wasn't fit to run.
If this was the reactor, and the vessel was out of tolerance, it could be fatal to the project, depending on what you're looking at. It at least would be a huge delay, because you wouldn't have to just replace the vessel. You'd have to do root cause analysis about how you ended up in that situation in the first place to make sure you don't end up there again.
Setbacks like this are exactly why nuclear companies rigorously test their tech, and why they face such intense regulatory scrutiny before ever turning on a reactor. The big question is, can the industry navigate this regulatory process and build reactors quickly, affordably, and at scale? Kairos set out to try. I'm Lara Pierpoint, and this is The Green Blueprint, a show about the architects of the clean energy economy. We've already invented most of the solutions needed to decarbonize the global economy, but many of those technologies are not yet commercial, and they need to get financed and built at scale. We don't have decades to get them commercialized. We have years. This week, we're talking with Mike Laufer, the co-founder and CEO of Kairos Power, about trying to drive down the cost of nuclear with a first-of-a-kind technology and a highly iterative development approach that upends the traditional model of building nuclear.
I tend to be a positive person, so it's setbacks or learning experiences, and that's why we're doing the iterations, is to kind of smoke out those weaknesses or those potential failure modes at the point where you can still recover.
When Mike Laffer and his co-founders launched Kairos in 2016, they started with two well-established technologies. One was high-temperature gas reactors, and these use a fuel called TRISO, basically tiny uranium pellets.
Basically like poppy seed size, like kernels of uranium, and then you put like different types of graphite and silicon carbide layers on top of that. That little particle basically provides like all of the functionality of the big concrete structures in the light water reactors that are, the major source of nuclear power today.
The other technology they were exploring, salt reactors, cool the fuel with a bath of molten salt called FLIBE.
It's a great heat transfer. The fact that the melting temperature for the salt is, in like the 400s, like we can't get the salt hot enough to like stress the fuel in the way that you could theoretically stress fuel in other reactors. So we don't have any scenario that can push the fuel anywhere near where it might actually fail.
The first big unusual thing Kairos did was to combine high-temperature gas and salt designs, something no one had attempted before. The combination has the potential to strengthen the safety of the design.
We have the salt as a backup barrier, so if anything happened to get out of the fuel, the salt has this tremendous capability to absorb basically anything that can get out. So that combination means that, hey, as long as I basically keep like a pot of salt with the fuel in it, nothing's really going to get out of the system. And so that's like a really different starting point from thinking about the safety of the reactor.
Like many nuclear startups, Kairos prioritized passive safety. That is, systems designed to work without any human intervention. And of course, Kairos was thinking about the safety and regulatory process for its nuclear reactor. But the company, unlike many other nuclear startups, was actually spending the majority of its time focused on getting good at building all the non-nuclear parts of the system. This is to say, all the parts of the system that don't actually need approval from the Nuclear Regulatory Commission.
The systems that are needed to ensure that you have the combination of fuel and coolant in the system is dramatically reduced, and they have a reduced footprint. That means that what the NRC is focused on in terms of just the physical area of the plant is much smaller, and things that are really important to safety in conventional reactors they don't serve any role. So they can change and they can evolve in design and build and function, but they don't have to trigger any type of regulatory review process.
Mike says this is a huge benefit. It means that Kairos can focus on non-nuclear demonstrations and developments. But back in 2016, when Kairos launched, people thought this was a crazy idea.
Now people are finally catching on that say, if you build the non-nuclear version of it, you can go much faster, you can learn, you get the information. So others are kind of following along and kind of copying that model. But at the time, it was really novel to build these big non-nuclear demonstrations in order to have us go faster in that learning cycle.
Kairos studied other capital-intensive, highly regulated industries. Think pharmaceuticals and rockets, like SpaceX. The lesson? Shorten nuclear's decades-long, multi-billion-dollar development cycle into something faster and far less costly. And after more than 8 years of work, Kairos pulled it off, landing a major commercial deal with two heavy hitters.
The Tennessee Valley Authority, Google, and California-based Kairos Power announced a collaboration today. TVA will eventually buy nuclear power from that plant in Oak Ridge, which will then supply up to 50 megawatts of energy to TVA's power grid. That grid powers Google's data centers here in Tennessee and Alabama.
So how did Kairos manage to build a first-of-a-kind nuclear reactor and land a deal with TVA and Google, all within a single decade? I talked with Mike about Kairos' journey, including 3 engineering test units, a demonstration reactor, and a commercial reactor, and the challenges it faced along the way. But first, I told Mike about my first time visiting Kairos. I want to start actually by telling a quick story, which is that I came and visited Kairos really early on when you all had just moved into your space in Alameda with this gigantic, like, airplane hangar-sized warehouse. And when we walked into the warehouse, there was a table, and it had this like plastic contraption in it that had a whole bunch of like miniature ping pong balls in it. And it was when you all were basically experimenting with the TRISO fuel and exactly how the TRISO fuel was going to be moving through the system and that sort of thing. So super awesome classic example of like a non-nuclear sort of benchtop approach to doing some real experimentation. I came back about a year and a half ago. And the airplane hangar looked a little bit different. It was now full of all these clean rooms. You had like 20 people. You're laughing because you know exactly how it looks today. There are experiments everywhere. There's all kinds of really cool stuff happening. The amount of equipment is astonishing. So walk us through kind of how this worked for you. Did you know from the very beginning that you wanted to follow this iterative process? Did you know from the beginning that you were going to do a whole lot of non-nuclear work first? How did you really get through your paces as a company in those early stages leading up to your decision to build a non-nuclear engineering test unit?
It took us a while to kind of figure out what this was going to look like in practice. Your story about like those original tests, there was kind of like this existential moment where like we have the infrastructure, we have this vision, but like we have so much to do, right? Like when you're starting off, like we got to design a new nuclear reactor from scratch. Like where do we start? And we've got, I don't know, we probably had 80 people at the time when we moved in 2018. It's like, what do we focus on? It was like, all right, well, what can we do? Like, we're going to focus on this one particular area, basically how we get pebbles out of the reactor. And we were going to put 2 teams on 2 parallel tracks, and we're just going to have them work through cycles really quickly. And we're going to see how that process works. You must have seen one of those teams working through when you came through. I think what was really crucial about that was we're trying to like interpret what was happening from SpaceX with their iterations through the rocket development, trying to incorporate learnings from agile development, which really has a lot of basis in software. When you're working with hardware systems, there's just going to be things that are different in terms of trying to do the iterative process. And so like those early experiences were really, really an important validation that yes, this process can work, but it gave us a lot of insights into the key things that are going to keep people focused. You can't just say, all right, go do these like 100 different iteration loops and figure out what you're going to do. The most important part of the iterative process is to understand what you're trying to accomplish in any given loop and defining how far to go. Like you want to go far, so you're pushing, but not going too far. We're constantly adjusting the scope of what we're trying to do in our development tests, which sounds simple, but engineers and nuclear engineers in particular like to have everything like mapped out. It's very hard to train people to do that. So we've put a lot of investment in figuring out how to adapt that process for us. And a lot of it really did stem from that early period where we were trying to just figure out how do we do this.
So let's talk about your decision to build a non-nuclear engineering test unit. So you'd been doing a lot of this iteration, and then you're coming to the point where you're ready to build a more complex sort of proof point version of your system. Was it always obvious that you were going to do something that was a non-nuclear demonstration, and was everyone immediately bought in? Or did you have moments where you thought, maybe we should move immediately to something that actually has some nuclear fuel in it?
So there was not one mind when we're going through this decision process. So we had this timeline, which was like 2018 to 2030 to get a commercial demonstration reactor up and running. And that timeline is just, it's like forever in terms of engineering. And we wanted to create big things that could be done in more like 2 to 4 year cycles. And if we do non-nuclear systems, we can go faster. That's a huge advantage. The problem is like, at that point we had essentially a commercial design that we were working on. We didn't want to build something that big for the non-nuclear system. So how do you scale down and what do you define as what you need to actually do in that test? And so we basically said, all right, well, we want to, the scale has to be relevant. So it's basically about half, the length scale is about half as much as the commercial reactor design at the time was. So the first point was, it's an opportunity for us to go through iterations of all the major systems in the reactor. We basically trained a whole generation of Kairos engineers around the whole life cycle of a major system. And in the nuclear space in particular, because there's so few build opportunities, there are a lot of people who just have experience in a very narrow band of that development cycle for the technology. And when you just do that one step, 20 times, you're missing so much about the overall cycle. And so the value of even relatively junior engineers going through that whole cycle for one system provided just a huge knowledge base. The other part of it, which was really crucial, we knew that we would have vertical integration as a key part of the Kairos strategy, but we didn't know what we would need to manufacture and build ourselves. The approach was, well, this is a non-nuclear system. There may be some gaps between that and the actual reactor. If a supplier could deliver for what we needed for ETU, maybe they could deliver what we need for Hermes. We'd have to test that or future reactors. But if they couldn't deliver what we needed for the non-nuclear system, there was no way they'd have any chance of delivering what we needed for Hermes. So we're actually able to screen out a lot of potential vendors that we could have spent years and huge amounts of effort well, can they do it? Can they not do it? It really just gave us that data point. The other side of it was like getting to operational experience is really important, and how everything fits together in an integrated system. You always have surprises that pop up then when you test all the pieces separately. We built the engineering test unit over the course of 3 years and built and operated over 3 years. And that whole life cycle of experience, it's the world's largest FLIBE system. It will be the largest FLIBE system until we load salt into the second engineering test unit that we're building right now in Albuquerque. So those are the key goals.
I love this. Okay, you mentioned that at first it was the engineering test unit, and then it became ETU 1 of 3. So can you tell me when and what happened with the first engineering test unit? Like, when did you know that this was actually instead not going to be your only engineering test unit?
Yeah, so I think this is like 2019, 2020. There's always been kind of this question, well, the iterative process is like start small and then go big. What would be the merits of doing a smaller reactor first? And so now Kairos is building the Hermes reactor in Oak Ridge, Tennessee. The Hermes scale is actually derived off of the scale that we chose for the engineering test unit. And part of that was, hey, if we want to move fast on a small reactor, we should leverage the engineering at the scale that we're already working with. So that's going to make it easier, going to make it faster. The other thing, which was, I say a lot of things about what Kairos has done with great pride and what we're going to do with a lot of confidence, but doing nuclear power is challenging. And the requirements that go into a nuclear vessel, I don't think there's any other system quite like it in terms of the chemical environment, the temperature, the radiation, and all the hardware that just needs to be packed into a really tight space. And we basically said, we're not sure that we can go straight from this smaller scale non-nuclear system to the full scale commercial nuclear reactor design. So we're going to do a smaller reactor. And the goal of that one is going to be, let's be as prototypic as we possibly can for the reactor system. A lot of other things kind of fell out of that. One of them was just a very practical reality. We're going to put the second engineering test unit in the same space that we're putting the first engineering test unit. We did ETU1 as a stick build. If we have to wait for ETU1 to be fully decommissioned and removed, and then go in and build, it's going to take a lot longer for us to do that. So, hey, we know we want to move to modular build. Everyone's talking about this. We know this is the way to go. Let's do ETU2 as a modular build and train that capability, develop that capability. And so we stood up a facility to do modular skid fabrication and integration at our campus in Albuquerque. We've got over 30 skids. Those are now being installed. There's a lot of learning. Like, people talk about SMRs. M is the modular, part of that. And they just assume that, hey, they do modular build all the time in oil and gas and chemical industry. Like, it's not going to be that big of a deal. Well, one of the key lessons is like that things that people assume are going to be easier are often way harder than they think. And so we have a third engineering test unit, which is also under construction in Oak Ridge, Tennessee. It's a little bit different. It's not going to have salt in it. It's really a low hazard facility for maintenance and operation training, as well as demonstration of civil construction interfaces. I'd say a lot of the benefit for having ETU3 was we could tell our engineers, like, you don't need to worry about solving that like all the way in engineering test unit 2. You can leave some uncertainty because we've got the third one. And what we found is that we've got enough learning and enough progress for ETU2 that we feel we can jump from that system to the Hermes reactor with high confidence.
That's super interesting. Okay, so you've got engineering test unit 1, which you've built, and then it makes sense that you're moving up in size with your engineering test unit 2, and then at the same time, you're staying small in size while starting on the nuclear side with your Hermes reactor. And then you're also building engineering test unit 3. So fundamentally, you're building 3 things right now. So tell me a bit more about that. Is that challenging? Is that creating any, challenges within the company, like competition for resources? Do you ever get pressure from investors who are kind of like, hey, what are you doing building all these things all at once? Let's do this more serially so you can incorporate the learnings. How have some of those tensions come up?
Well, zoom out even further, we're building a whole lot more than that too. So we're building a salt production facility in Albuquerque, and we're also building fuel production infrastructure. So vertical integration, in-house manufacturing is central to Kairos' strategy. It's really important both to the development strategy, but also to the commercial strategy. So from a business perspective, when we look at like bringing something in-house and doing it ourselves, it's not just that we're controlling costs and schedules when we do that, we're also capturing value. So our business model is the more we do, the more of the revenue that Kairos captures from the project. But for a company that has manufacturing capabilities and production capabilities, this is actually a lesson in the iterative process that's different from, I think, maybe conventional best practice. In a perfect world, you could go through that life cycle of iteration, get all your experience, and have it cycle back through and then build the next one, right? And maybe even in the extreme case of rockets, your entire product life cycle is like 30 minutes. And so you can take that experience and you can go and incorporate that back into the next cycle. The lifetime for reactors is decades, right? So you can't do that. The other side of it is when you have the overhead or the investment in the manufacturing capabilities, if you just wait for that operation experience, even at smaller timescales, you have a lot of people just sitting around not really doing anything. So for us, basically just have build as the thing that happens continuously. And so keeping that build machine just heavily utilized and active is the way that we're going to get the most efficiency in terms of as an organization pushing things forward. And so there's nothing to do with nuclear. That's just trying to run a lean organization efficiently. And just that a lot of people don't think that's really possible with a lot of nuclear development because the systems are so big, they're so expensive. How do you do it? That's just, you got to shrink the problem into much smaller scale bits that you can do that with.
Yeah, I mean, this leads to another question I have, which is about geography, because fundamentally, you're headquartered in Alameda. You built the first engineering test unit in Albuquerque, New Mexico. You're now building Hermes and Oak Ridge, along with your ETU-3. So what led you to decide to have these different locations, and how do you manage people across all of this and make that cross-pollination happen? Like, in my mind, I'm envisioning something like 1,800 Slack channels for your company, or some ungodly way of keeping in touch. So what does that look like?
Yeah, there are a lot of Slack channels. I mean, I think that in retrospect, there's a rationale about why everything is where it is, and it was deliberate. The sequencing of sites is really important, and each site serves different functions. In the early days, there wasn't an obvious place where we could find the people and put Kairos and just do everything. There are capabilities that we can find in people in the Bay Area. There's great software development. We have a range of different schools to pull from, but we were fundamentally limited in the size of how big we could do things here. And so we needed to find another site to do that. Albuquerque was the place to land. We were already familiar with it. There's an ecosystem with the labs there. There is kind of like a nuclear development world in New Mexico. But then it was kind of like, well, we want to build and expand and do more there. And the logical place to put the next thing is either next to the last thing you built or next to the thing that you plan to build in the future. And both of the Albuquerque sites and the Tennessee sites fit that bill perfectly. So Alameda has become the hub for kind of the rapid early development testing for new ideas. But also it's really the hub for a lot of the validation testing that we're doing along the original vision for our models. So we have a lot of our kind of simulation software teams here, as well as the testing teams, and having that integration provides a lot of value on that side. Albuquerque is really more around larger scale testing and manufacturing and across the board for reactor systems, fuel and salt, and all that infrastructure. But what we're building there is mobile. The skids can be shipped. So the future builds are not tied to that location. And then Tennessee, there's obviously a very strong historical legacy for nuclear development in Oak Ridge. The national lab there has tremendous capabilities, but it really just kind of makes sense as a hub for where we're going with the nuclear construction and nuclear operations. And so having that vision for how all the sites fit together, it's not easy standing up sites and kind of trying to get them aligned around the same culture and getting every people operating the same way. It's not easy to travel between Oak Ridge and Albuquerque, New Mexico. We acquired the site in New Mexico in February of 2020, and part of the appeal of Albuquerque was all of the back and forth direct flights from Oakland. When COVID hit, we were stuck, right? And so we had to adapt. And we're a hardware company, so being there in person matters a lot. And getting our teams moving back and forth has been instrumental in those facilities. But our team is really dedicated. They put in huge amounts of effort, and people really just want to build something. They want to be contributing towards the first reactor that's going to get built, that's going to come online. And so, like, the travel is it's not great, but people know the value that it provides, and they're all going towards the same goal, and they know what that is, and are hugely motivated to put in kind of huge efforts to make it happen.
Yeah. Well, and so you mentioned that it feels really good then when you're kind of ticking on all pistons. You've got the cross-pollination among all these sites and folks working together. So it sounds like it's great when it works well. But you also have moments that are challenging, right? Like you had an issue with a reactor vessel at one point during a particular test. Can you talk about how you overcome some of the things that are maybe not going the way you had hoped, or, posing some challenges that you didn't quite expect?
Yeah, so there are always challenges, and they range from minor setbacks to really good head scratchers. For the engineering test unit 1, we sourced the vessel from a shop in Southern California, very reputable shop. The costing was very reasonable. Our team was integrated in the design. Like we had a very good relationship with them. It's an ASME certified pressure vessel, so it needs to go through a series of testing, hydrostatic pressure testing, to make sure that it can actually remain intact within the design basis. So they did this testing. They happened to do it horizontally. The vessel was laid down on its side, which was not a great thing. So talking about like the learnings, we have a database that gets filled with all of these lessons. So don't do pressure testing on with the vessel on its side.
And that brings us to the reactor vessel mishap from the top of the show. More on that after the break. So Kairos is testing a reactor vessel in its engineering test unit 1, and they run into issues.
You have to go to much higher pressures than the system is actually operating. So we had distortion in the vessel, and the vessel ended up out of tolerance. What do we do here, right? This is critical path. The vessel needs to be installed before we can install internals and everything else around it. So like, how are we going to remedy the situation? If this was the reactor and the vessel was out of tolerance, you would have it could be fatal to the project, depending on what you're looking at. It at least would be a huge delay, because you wouldn't have to just replace the vessel. You'd have to do root cause analysis about how you ended up in that situation in the first place to make sure you don't end up there again. In this case, it was, is there a safety issue? That was the first question. Like, can the vessel be used, and will it be safe? And so we looked at the results, and it was like, yeah, the vessel is going to be fine from a perspective of safety. We're not worried about the integrity. Now, how do we make everything fit? And so in parallel, and there's a sleeve that goes into the vessel, and then inside that sleeve are like 300 pretty large, like a couple 100-pound graphite blocks that get assembled into this pattern. And there's the pebbles go into, through the blocks. There's reactor cores in there. So there's this really complicated graphite assembly that goes in there. And you want to have everything fit together really well, because if you have big gaps, if a lot of salt flowing where you don't want it to flow. So how this all fits together is really important. We'd made in parallel the decision that we were going to do machining of the graphite blocks. The fact that we had the machining capabilities on site allowed us to process nearly all the blocks with minor modifications to adapt to the as-built geometry. We're able to move forward, install them, and keep everything on track. And there are many things that I'm thankful for, but I'm always thankful for, if the iterations are set right, you can have things that will be setbacks. I tend to be a positive person, so it's like, setbacks are learning experiences, and like that's the whole reason why we're doing the iterative development process. I'm thankful that we had that experience with that system, and it didn't push forward to Hermes. So setbacks happen, but the way that they fit into the process is, that's why we're doing the iterations, is to kind of smoke out those weaknesses or those potential failure modes at the point where you can still recover. And if we can do that, then everything is working well. if the failures happen, the point where you can't recover, that's the end of the road.
I feel like there's a metaphor in here somewhere. It's like your reactor vessel is squished, so it's time to go and machine some squished graphite blocks as a result, and then you're off to the races again. I love how there's adaptability that's really in that. Well, so you've mentioned a couple of times the importance of the vertical integration here and the fact that you do have these capabilities in-house, and it seems like there are plenty of things for which it's a no-brainer, right? That, as you mentioned, in the nuclear industry, you've got a whole bunch of things that are not manufactured in large quantities and that have all sorts of really, important specifications around them. Are there any moments, though, where you find yourself asking the question, for this particular component or for this particular system, should we outsource it or should we build it ourselves? Is that a constant tension that you're facing, or do you almost always in those cases just default to building things yourselves, or how do you think about those questions as they come up?
We have more confidence now, certainly, than we did years ago. The team understands the benefits of taking ownership over not just the design, but the build. There's always a decision, and as the needs evolve, I think the same principles still apply. And one of the key things is try not to stretch too far. And so, if there's something that's new or dramatically different, it's usually beneficial to start off at least with a partnership with someone who has some part of the key knowledge. And so on the pump, we started off, we have a partnership with Barbara Nichols. Kairos has absorbed more capability ourselves, but it was a really productive partnership. We have found partners along the way that have been great to work with. And if that works out, that's great. Like we don't want to do everything ourselves because it adds to the list of things that need to be done. Right now, we're pushing the boundaries on the civil construction side, which is this is much bigger scale than all the other things that we've been setting up to build. So right now, one of the exciting things that is emerging is the opportunity around precast concrete, which is really just potentially completely transformational in terms of how we build these buildings. Totally conventional and a lot of non-nuclear construction, but how do you do this for the nuclear requirements is sort of a big open question. We have, again, the iterative approach, so we've been working in collaboration with Oak Ridge, with Bernard, with other vendors, looking at how to do 3D printed forms, and it's kind of generated a lot of attention because it's been moving really fast, really just the last couple of months through a couple of iterations. We're involved in that, but we're not saying, hey, we're not saying we know how to do it the best ourselves. We recognize what we know and what we don't know. We have to be humble. We can't do absolutely everything. We need to find the partners that are going to be able to work with us as well.
Okay, so let's talk a bit more about the Hermes reactor. So again, for folks who are following the nuclear sector here, you've got your engineering test unit, no nuclear fuel in that. Now you're building Hermes, which is a legit nuclear reactor that's going to have nuclear fuel in it. Can you talk a little bit about what your engagements are like on the customer side? Are you planning to actually produce power with this first Hermes unit? Are you planning to sell that power? How are you bringing utilities into the conversation? Because I think this is one of the other big hangups for the clean tech sector is to figure out how do you actually bring in customers, particularly on these first of a kind endeavors?
Yeah, so Hermes, we worked through the plan to do Hermes in 2020. It was in conjunction with a DOE proposal that was kind of the seeds of the Advanced Reactor Demonstration Program. Our approach was, this is going to be our plan, and whether we get the DOE award or not, this is our plan. We were selected for a DOE award for the Hermes reactor. The idea was, let's do the minimum viable reactor. And so take out the things that don't really need to be there and just get to the point where we can design, license, build, and operate an honest to God nuclear reactor. And we've gotten huge amounts of value out of that. Even in the construction phases now, we give us real data, real cost numbers that are going to project forward of how much our foundation is going to cost for future reactors. We have really good knowledge about what those are actually going to be based on the experience we have from even to this point in time. So fast forward, we got a construction permit from the Regulatory Commission, first advanced reactor to submit and get. We did it in just over 2 years. That was a huge accomplishment, and again, something people thought was going to be really, really hard and challenging, and we were able to navigate that process very efficiently with strong technical content and just a lot of hard work from the team. there was a window of opportunity to do an application for another one. So, hey, if we say, hey, we have this design, if we can further leverage it and not change the reactor that much, and we can attach power system, we have an opportunity to continue that build cycle and do it at the site. We already have the site characterized, and so there was an opportunity. We did that. We did the review on Hermes 2, and that review came through. Now we have the opportunity to expand there.
Okay, so very cool. And I think just to name the headline here, which is that you now have 2 reactors that have gone through the Nuclear Regulatory Commission process, which is actually a really big deal, especially because that's something I think that investors in the nuclear world have been nervous about, is would the regulatory side of this take too long? And you're already showing that this is possible, and you're underway building one of them. I'm going to ask you a question that is going to make it really clear why I will never be as popular as Joe Rogan, and that is to hang on to something really critical and interesting to me that you just said, which is that you had a novel contract with DOE. And while I am more interested in most than DOE contracting structures, I think let's talk about this for a second, because it actually is truly novel and really important. So can you say a little bit about historically how DOE has done contracting and how they've interacted on big projects like this, and what's different about the particular award that you got from DOE?
Yeah, the quick summary there is the conventional DOE contracts. They're different types of agreements that provide funding into companies. They've been doing these for a long time. There are a lot of companies who have all the machinery in place to manage these contracts, but it inserts a lot of overhead into the business practices. There's all kinds of requirements around reporting and procurement requirements, and this is all motivated from the very genuine desire to make sure that DOE is a good steward of taxpayer dollars. Right? There's everything is good in this. The problem is that layering in all of that process makes it very hard for organizations to be agile and flexible, and in part because nuclear in particular wants to have everything mapped out. DOE also wants to say, well, if you're going to go from here to there, what does that whole program look like? Exactly what do you need resource? Well, they want to know all those details, but for Kairos, we don't know all those details up front. It doesn't really fit with our development process. And so we looked for sources of innovation. The best model we have, and it's a really good one, NASA has different contracting issues than DOE, but they had like the cost plus contracts on various services where contractors, they basically get payment and then they get more payments when they're overruns. There's not really the same level of ability to control or have accountability on those. There was an amazing program about 20 years ago, the Commercial Orbital Transport Service Program, COTS program, which basically the philosophy was buy a ticket, not a rocket. And there was great influence from like the venture capital world, and basically get NASA to think like an investor, not like a government entity. This was put in place. SpaceX was one of the original selectees. There was another original selectee that actually failed, and they canceled the contract. They weren't able to meet some of the milestones. And then Orbital Sciences came in, and they were actually a second successful recipient and were able to go through this process. The key thing is, and this is kind of the fundamental trade, you use milestone-based payments. And so instead of paying for work, you're paying for the results. We've had a number of these. We've had 2 this year for our vessels that we installed for engineering test units 2 and 3. It basically allows more flexibility for Kairos, but it provides the accountability for DOE. And I think this is the perfect type of trade in terms of maintaining stewardship over federal tax dollars, but allowing novel, innovative companies like Kairos to keep doing things in an innovative way.
Yes, as someone who has the battle scars from the minutia of the blocking and tackling and recording and budgeting and hourly tracking of who is spending what kind of time on what, I agree with you. I really hope that DOE does more of this in the future. Okay, so let's get into Hermes 1 and Hermes 2. So you decided to build Hermes 1 at the same scale as your ETU 1. It's not going to produce power, but Hermes 2 is. So talk a little bit about... Well, I guess first of all, let's talk about Hermes 2 and the power production opportunity there. Is this power that you're going to be selling into the grid? How are you thinking about that in the context of your customer base?
Yeah, so with Hermes 1, we really wanted to be true to the idea of a minimum viable product. And product without electricity, maybe that doesn't quite match up perfectly. But we really needed to just prove that we could deliver a nuclear system. For us, really the demonstration was around the ability to deliver the nuclear heat and really just focusing on what are the essentials. The opportunity for Hermes 2 was, if we were going to build this reactor, well, why don't we go quickly for permits to build more of them? And because our architecture means that the things that are important for safety in the regulatory space is pretty narrow, we can actually change the design in a very basic way for the power generation side of the system. And the feedback loop into licensing is almost nothing. So the technical review on that reactor is basically, for the things that you're adding to the system, does it have a feedback loop that's going to impact the safety? And the NRC basically concluded, no, there's no feedback loop. So the safety case looks exactly the same. The original decision to pursue Hermes 2 was, hey, we're going to be building one of these reactors. Like, let's seize on this moment and keep building. Again, build, and do more of them. Turns out we've been learning a lot and gaining confidence in certain aspects. And when we think about doing the evolution design, there was only going to be one Hermes 2 because it wasn't really quite viable as a full commercial product offering. We'd have to scale up. And so as we're thinking about it, well, the question came up, what if we could make Hermes 2 essentially a single unit reactor at essentially the full scale system for demonstration? Just basically convert it into a demonstration reactor for our commercial scale product offering. We were kind of looking through all the different applications here, and we actually concluded that, yeah, we can do this. And so we were kind of working through this process and in parallel working on the commercial side. And so we have a really exciting announcement that we just had with TVA and Google that kind of puts together a novel commercial arrangement around this new evolution of the plant itself. And so it really is kind of a novel structure that allows all three parties to benefit from the process. And it kind of allows Kairos to develop the project, Google to get the clean energy attributes, and TVA to get the power in a way that really is kind of, it makes everything work in a new way. And innovation also happens on the commercial side, not just on the hardware side.
Okay, and so what comes next? What are you going to build after all of these reactors? When are you going to start building these things commercially all over the place? When are you going outside the United States? Couple minor questions about your roadmap ahead.
Yeah, so I'll kind of go back to the context of our agreement with Google. It provides essentially the process of how we're going to not build just one reactor, but multiple reactors. And so when we look at the 500 megawatt total capacity for Google, we're looking at kind of the 50 megawatts on the Hermes 2 side. And then we're looking at basically 6 more reactors to deliver at 75 megawatts each as kind of an evolution of that initial demonstration in Hermes 2. So if I lay out the plan for the next 10 years, that's pretty much what Kairos needs to deliver. That's a lot to take on in terms of the number of builds. But if we can build that sequence, it really allows us to realize most of the benefits of that learning curve. And we see the ability in just those first, essentially 7 reactors, like dramatically bringing down the capital costs, 40, 50% is possible. And then we're staged for the second half of the 2030s to scale from there when we really have things dialed in and we know what we're doing. And I think about this a lot, actually, because there are lots of examples of different failure modes in the energy space. But one of the scary ones is where everything is looking great. You're getting huge amounts of capital and say, hey, if I can do more, then I can get to more revenue faster. Like, that's going to be great. Like, why would you not do that? But there are cases where trying to do too much too fast can be a failure mode. So the Northvolt example is a really important one where I have to do the thought experiment. If they had not tried to do as much, tried to build as many plants, if they just focused on one plant doing it really well for the initial execution, like would that have been a more likely model for success? So for us, it's being very ambitious to try and do a lot, but also being a little bit cautious to make sure that we're not oversubscribing until we know that we can actually deliver what we're committing to.
Always a challenging balance. Well, that is a fantastic note to end on. Mike, thank you so much for joining us here on The Green Blueprint. This has been a fascinating conversation, and we really appreciate all your insights.
Lara, it's really been a pleasure. Thank you so much for having me.
Mike Laufer is the co-founder and CEO of Kairos Power. The Green Blueprint is produced by Latitude Media in partnership with Trellis Climate. The show is hosted by me, Lara Pierpoint. This episode was produced by Daniel Woldorff and Erin Hardick. Ann Bailey is our senior editor. Sean Marquand is our technical director. Stephen Lacey is our executive editor. If you'd like to suggest topics or guests for the show, send an email to thegreenblueprint@latitudemedia.com. You can listen to The Green Blueprint at latitudemedia.com or subscribe wherever you get podcasts. And if you have fellow clean energy or climate tech travelers who would benefit from the insights in this show, send them a link. This is The Green Blueprint, a show about the architects of the clean energy economy.